In kinematics, we have time, position, displacement, velocity, and acceleration. Of these quantities, time is what we call a scalar. That means it's just a number. It could be positive or negative, but it's just a number. Negative time might seem weird, but we could always choose our time to refer to some time before, but it's just a number, so it can be positive or negative. Now you might think position is just a number. It's I'm over here, I'm at 3 meters, but that over here actually implies a direction. Vectors have both a number, 3, -3, but also direction. It's -3 that way, or I'm moving at 3 meters per second that way. And so there's a direction involved. So this is just the number. This is the number and the direction. Okay. Because of that, when we're looking at adding some of these quantities together, we have to be very careful. And up till now, we've been talking about one-dimensional motion, which has only the direction has only come into play in being plus or minus. But if we have something moving to the left and an acceleration that's upward, that's going to affect it much differently than what we've seen before. So to be able to do two-dimensional or three-dimensional motion, where direction now has a whole different meaning, we need to know how to add vectors together to be able to compute final values. That's going to be our goal. A basic idea is that vectors we can indicate with an arrow, which we've been doing, but now I'll draw that arrow at some angle. Here, this might be my velocity vector, okay? And to indicate it's a vector, I'm going to now draw a little arrow sign over it, okay? And whenever I'm talking about the full vector nature, we'll need to be careful to indicate that vector direction. In one-dimensional motion, it's not that important because it's only pluses and minuses. But when we're having something that has both multiple components of motion, or vertical and horizontal motion, or into the page and horizontal, or any two combinations or more, we need to be careful to indicate those directions. So for example, in this one, if I choose a standard coordinate system of to the right being positive x and upward being positive y, then this would have an x component and a y component. They would come together. I could draw them like that, where the x and y are at 90 degrees to each other, and the total velocity is always the hypotenuse. So our Vx, which I'm going to put as a vector since we're using them to add up to be this full vector, these would then add up to be that. Now the question is, well, how big is this one? If this is 1 and this is 1, is this 2? Well, we can see graphically that that's not the case. What we have to do is add up the squares, because this forms a right triangle, and we know that for a right triangle, the size of the lengths, so I'm just going to write now, just we're talking about size, so no vector sign, the size squared of the hypotenuse is equal to the sum of the square of the other sides. So we have Vx squared plus Vy squared. Okay. Another thing to compare them is if we know an angle, which we often do. So if I describe that angle to be theta, then I could say that the cosine of theta is adjacent over hypotenuse, which allows me to say that Vx in size only, so no vector signs here, is equal to V cosine of theta, and then Vy, being the opposite, would be V sine of theta. And so I can relate the total magnitude, or the magnitude of the total vector velocity, to its sides or its components in the x and y direction, either through the sum of the squares or through our trigonometry knowing some angle.